In the example, we are given two linearly independent vectors like this. All we know is their magnitudes, and we have somewhat of an idea of what direction they are going to be. And we need to find a vector r defined as the sum of vectors a and b. So if we look at vector a, we can see that this is strictly composed of an x component. We know that it has a magnitude of 7, and so the system that I am using here is, for whatever direction an arrow points, we are going to have it rotating counterclockwise, like so. It's going to rotate in that direction. And so in the case of vector A, we can look at this as a degree theta is equal to 180 degrees. And numerically, if we were to say it is going clockwise, it would be negative 180 degrees. And so what we should have here is, again, A is made of, A's x components are going to be negative 7, 0. This is the x portion. And the y component of A is just the 0 vector. Hence why when we add these together, we are just getting negative 7, 0. And the magnitude of that is just going to be 7. Now, for B, we can see that if we look at its components, its x component is the 0 vector, and its y component is 0, 4. And when we add these together, 0, negative 4, when we add these together, that is what we get. Likewise, the magnitude of this vector is 4. So now, to get the coordinate vector of r, we are going to add a and b together. So this is vector a being written here, and this is vector b. And when we add these together, we add their components. We're going to end up with negative 7, negative 4. Okay, so we've got that. Now let's say we want to find the magnitude of r. What we will do is, just like before, just to be more explicit here, it would be like if you had 0 squareds in there, which would just be 0. And so here we are going to end up with, let's see, square root of, we've got 49 plus 16, 50, we got 65, I think, 59, so yeah, 65, square root of 65. So the magnitude of r is the square root of 65. Now, to find the, there's one more thing we're going to do here. We are going to use a trick where, let's say you have two vectors like this. In this case, we have two linearly independent vectors, and let's say this guy was b, or, just call them v1 and v2. When we're adding the vectors together, you can use a tail-to-tip method to get that resultant vector. So likewise, we would do the same here. You're just going to imagine that this vector here is moving over to here, and then we draw from the tail to the tip. So I should have a resulting vector r out here. Let's see if I can get this. Let's see. I'm just going to eyeball it. We should expect it to be... we would have something like this right here. It's about right. It's not perfect. We'll see when we actually do some computations. And so this will be our vector r. Okay. And to touch up on what was talked about before, we know that sine of theta is equal to opposite over hypotenuse, cosine of theta, adjacent over hypotenuse, tangent theta is opposite over adjacent. And so if we're just going to look at this triangle we have here, we have theta, we've got this, we've got our opposite, we've got our adjacent, we've got our hypotenuse. So to find theta, we are going to use this one. And so what we do is we can say then that tan theta is equal to O, in this case, will be the magnitude. And if we're, doing a one-to-one mapping of our logic here, that's going to be the magnitude of that, just this length here is 4. And again, that matches up to this here. And then, where were we? Over here, we have this being 7, right? And so that means that when we are doing this, we're going to have this. Tangent theta is equal to 4 over 7, and therefore theta is equal to arctangent of 4 over 7. Now, if I do that into our calculator, we will get times 180 divided by pi. We're going to get, this is approximately equal to 29.7449. That's what my calculator gave out. Degrees. Okay. So if we jump back up to this drawing here, right, if we're sticking to my convention of we're going clockwise from here, and we were to rotate this, let's just round up to 30 degrees. We're going to get about to 30. And that lines up quite nicely with what we did with the graphical method. So that would mean then that there is if this was to mirror across here, we would have theta is equal to approximately, if we're rounding up, 30 degrees. Now we know from this point here to this point that that's 180 degrees. So what we need to do is we actually need to add 180 degrees to get the accurate angle here. What is this guy? So if we add 180 to that, we're going to stick with that more accurate number, this more closer approximation. So we're adding 180 degrees to that. And what we end up with is approximately 209.745 degrees. So what we can say then about this vector r is that the magnitude of r is equal to the square root of 65, and the direction is 209.745 degrees going counterclockwise from the x-axis, which we have there. It matches up with the image. So where I was coming from with when you saw this cosine, theta, sine theta, stems from when you parameterize the surface of a sphere. So we know that when we have a sphere, or let's see, I'm not the best drawer here. So we have x, let's put x here, y here, and z here. And let's look up a quick convention that we want to use. Here we go. So this is the one I want to go with. Okay. Yikes. This does not want to... Okay, nope. maybe. There we go. Okay. All right. So where was I? So I'll add another link that'll show a thing that I was using in 3D graphic for this. But when I was doing this, let's pull this up on my computer. What was I doing? Okay. So I had a vector like this. We're just going to stick with cosine theta, sine theta, and we're just going to let the z be 0. And now, for the animation that I have on my computer, which I'll add here later, when we would have both of those at 0, and we would range theta between 0 and 360 degrees, from a top-down view of that 3D space, you would have a point that would move along like this, and if you move the slider back, it would just go back and forth between them. And the distance from the origin here was determined by the r value, which in this case would be kind of like our magnitude. So you can kind of think of it the way that I'm viewing this as in the form, the coordinates are theta. What do we call these? Those are polar coordinates. And as you can see here to the right image, that it uses the exact same setup that I was using, where the x component was equal to r cosine of, I believe this is called rho, I could be, I don't remember what this is called, this thing, r cosine theta, or cosine whatever that is, cosine theta, yr, and then you would have cosine of that same value, cosine of, sine theta, and then for the z component, you were going to have just r sine this thing. And so in our case, again, we're working in 2-dimension. So what that would mean is that this guy, in our case, is set to 0. And we know that cosine of 0 is equal to 1. So then these will simplify down to r cosine theta, r sine theta. Sine of 0 is 0, so that would just be 0. So what you would end up with is a vector that looks like this. If we're viewing it in 3 space. And let me think, what else did I want to add here? So this was my thought process to how I was doing it. So when we would have r be the magnitude, so we were talking about a polar coordinate system. So, if we were to, view coordinate vectors from, they would be like this. You would have r, that's, the order of these might be swapped. I'd have to go look at how I'm setting mine up again. So if we go to, let's just do spherical. Let's look at just spherical coordinates. Okay, cool. So it's this wiki is using the same convention that I have here. All right, so we have r theta. Let's change this up. So going back up to our diagram, we would have a theta value. And so if you had, an x component here, a y component here, and then I'm not so good at drawing this. Let's find that other good drawing. Essentially, I'm trying to draw this. I can't draw on the screen here, but this drawing here. You see that you have that theta angle here, which indicates counterclockwise. So in this case, this direction here is counterclockwise. And then any angles that you are creating when you drop, where is it? I'm sorry, when you raise it, the convention that we're sticking to is that's like, let's say we have some points. I will try to do my best to draw this in 3D. So we would have some sort of point that lies out. Some point that lies out here. The line that you have that is extending out from the origin, it's rotated by this much in this direction, counterclockwise, and then it's rotated upward to that point there. And again, that's what we're seeing here. So the way that I had this set up was that this was a measure of counterclockwise from x, x axis, and then this here is a, if we're looking at, pretend that this is our z and this is our xy plane. No, what am I thinking? Wait, so you got xy plane, y. Right. Okay, so this is if we're looking at it head on. So this would be like our x here, and then our y would be popping out at us. Right here, just like this is y popping out at us. Then this guy here, like we had that yellow point earlier or whatever, this would have been this, which would have been how much you're raising it up off of our xy plane. Yeah, so this was the approach that I was taking here with that. And so I just want to reiterate that I know that when if we were to take R and break it back down into its x and y components, like if we're just going to look at A was pointing out this way. You had A going out that way, -7. So you could say it rotated 180 degrees and it extends out 7 units. And then this guy, sometimes I shortcut stuff with negative degrees. So I said, instead of going, we're going -90 degrees. And that extends -4 units out. And so in these cases, you can see that you have 7 cosine of 180 degrees equal to -7. And then in this case, you had -4 sine of -90. I'm sorry, that'd be 4. 90 degrees, which would be -4. And again, this was what? This was vector A, this was vector B, but A was made up of, again, it was made up of these here. And so I'm not trying to view things through this sort of perspective. And the reason why is because I'm trying to use this type of idea combined with how you would parameterize the surface of a sphere, and I'm visualizing it like this. In this video, I'm going to start with some basic vectors and build all the way up to a coordinate system that we can use in three-dimensional space. So first off, let's say that we have two vectors that look like this. We'll call the green one A, and we'll call the blue one B. And the magnitude of each of these are going to be 1. And we're going to define a third vector, C. We're going to get to that in a second. Okay, one more thing I forgot. So vector A, if it has a magnitude of 1, it's going to be composed of these. We're going to have 0 in the x direction, 1 in the y. No. Yeah, like that, like I did before. I want to follow the pattern of like there being an implicit, we have a 0 vector, and that's just going to be 0, 1.
And then in this one we are having is made up of
We're going to use the graphical method here so we can see clearly the triangles that develop. So this is a graphical method where, again, if you have a vector, two different vectors, you're adding them together, the third vector is right there. So that's how I get that purple vector. So that's what we have graphically. And to find the magnitude, we want to know the length. So let's improvise and say that, this, we'll keep using that triangle, that this was A. Oh, wait, sorry. This was vector A. It doesn't matter, they're all the same size, and this was vector B, and then this is vector C. Becomes a Pythagorean theorem thing, where you know that A squared plus B squared is equal to C squared, so C is equal to the square root of A squared plus B squared. In the case of, they both have a length of 1, so we just know it's the square root of 2. So the magnitude of C is the square root of 2. Now when you want to find theta, we know that sine theta is equal to opposite over hypotenuse, cosine of theta adjacent over hypotenuse, tangent of theta opposite over that. Okay, so we are going to use this one here, and we know that tan theta is equal to, our opposite side here has a length of 1, this should be A, adjacent. Yeah. 1 divided by 1 is 1. Tangent of theta is equal to 1, so that means then that theta is equal to tan inverse of 1, which will be, it should just be 45 degrees. I know that off the top of my head. Okay. All right, and then, cool, so we've got that. Now, where was I going with this? Okay, cool. So now we're gonna go up a dimension. So we've got. Oh wait, before we do that, let's see what this would be like in spherical coordinates. Our resulting vector is. I'll just rewrite it down here. We have c is equal to a vector 1, 1, right? We know that x is equal to r cosine theta, y is equal to r sine theta. There's a lot of recurring themes here. So continue with that same thing. We have x is equal to 1. We're trying to solve for r. We know that cosine of 45 degrees is going to be root 2 over 2. Same thing goes for sine of 45 degrees is also root 2 over 2. And that leads us to agreed values of where r is equal to root 2. R is equal to root 2. Now again, these, if we're going to do these in, sorry, not spherical, we'll just say polar for now because we're not in 3 dimensions. If we're doing r theta, that means that we can write our vector c in the following way. We can write it as r cos theta sine theta, which will then be root 2. And we said that this was root 2 over 2 when evaluated, and this was root 2 over 2, which is equal to 1, 1. Okay, now let's go up to our 3 dimensions. This is our z-axis, this is our y, this is our x. And so let's just take what we already have so far and move it up into the other dimension. So we have extending out a unit of 1 in either direction on the xy plane. So the x plane corresponded to vector b, so xbya, xbya, xb blue, x, and this was vector b. What color do we make that? Green A. So instead of making it a green A, we'll say that A is the color yellow. YA. Okay, this was vector A. And then vector C extended out. Now I can't zoom on here, so this might be a little hard. So this right here was vector C. And that was theta going counter clockwise. From the x-axis. And that the x component followed r cosine theta, and that the y component was r sine theta in polar coordinates. I think this is where some problems were coming up earlier when this was being discussed. I'm viewing it through a different system. Okay, so we need to have some sort of way to capture z. Right, so we're going to look at this side view of where of that same thing, where this is the z, this is the x, and the y plane is popping out at us. I'm sorry, the y-axis. We have the xy plane and the y-axis. And so let's say that we had a point that extended out there, right? So it's like a coordinate vector, but now we want to add some sort of height to it. Up there. And if we were to draw a line from the origin, from the origin to that point, that line from the origin to that new point would then be a vector with 3 components. It would be if we added a z component to our same one. So on one hand, we have this dotted line here, which is the height. And if you look carefully, you can see that there's also another right triangle there. Now let's try to bring that over to here. So we had that point here, which was the tip of, let's make it purple. Make it a little more clear here. This was the tip. Let's make this purple. It's just, this was vector C here. And that height that I was trying to illustrate earlier is right here. Okay. And if we draw a line, like I did there as well, running from the origin to this other point, you can see that another right triangle forms. And we have a theta here as well. And C is made up of 2 vectors already. It's got the x component and the y component, and this is the z component that's being added. And let's do one other thing here. We're going to make this phi, because this is a different type of angle that we need. This is how much we're angling upwards from the xy plane. In this case, in this drawing, we would say it's from the x-axis. And so we already, I don't know why I'm getting so anxious right now. So we know that, what did we say the magnitude of C was? We said that it was equal to the square root of 2. So we can throw that up here. But how was that made? That was made from the square root of, we're just going to go with x squared y. Continuing along here, if I were to do a substitution on that, we would end up with this, and that comes from here, the Cartesian to polar conversions. Shorthand that is cart to pole, and we know that this is going to be equal to which is just equal to this, equal to that, where r is equal to our square root of 2, which is the magnitude of C. Yeah, so we went full circle on that. Okay. So let's pick a height. Let's say that this length here is 1. Then using that same theorem, what we will end up with is root 3, meaning that this side here is root 3. And then, okay, so we're going to continue with where I left off here. So let's assume that we do not know these pieces of information. And we are saying that a measure of theta is counterclockwise from the x-axis, and phi is a measure curving upward from the xy plane. We can see that the triangle that forms here will then have the projection of r onto here. That's one way to think of it, or we could still think of it in terms of right triangles. But we're going to think of it in projections because it gets a bit trickier when we get up in dimensions. So then that would mean that this side here is r cos phi. And then by taking advantage of some symmetry, which means that this one here, the rejection of r onto where I was pointing earlier for the projection, is r sine phi. Now once we have those, we know that we're working with vector spaces, and so they have to satisfy the 7 axioms to be considered a vector space. Just to list a few out, we have, associativity. Now, the reason I brought those up is because this vector here, which was a projection of r onto the xy plane, is going to be a linear combination of this vector and this vector. So we know that we have, we're going to call this vector here v1, and this vector here is v2, and we're going to call this blue one here is vector 3. So let's put everything together that we have. We have some constant multiplied by v1 plus some other constant multiplied by v2 is equal to v3, and we are claiming that the magnitude of v3, assume these are all bold-faced. I just don't like to write arrows everywhere. So we said that the magnitude of this, which was the result of a projection, was, we said it was this r cos phi. So now let's start plugging in more of our knowns here. We had C1, we're going to write this in column vector notation. Vector 1, with what we have so far, well, these all had R on them, but we can just divide it out of our system. I'll just put it here for now. Cosine theta 0 plus C2, and there's another R here too, 0 sine theta is going to be equal to C1 cos theta C2 sine theta, and where was I? Okay, so I'm running out of room here. To get the magnitude of that, we were saying that the magnitude was equal to R cosine phi based on the projection. So we're saying that that should be equivalent to, oh, there we go. There's the R that we're dividing out of our system. That's what I was tripping up about. We're dividing the R out of our system. So we're just going Oh, right. Here's how I can think about this. I think I have an idea. Okay, so if whenever we have some sort of root expression that has cosine squared theta plus sine squared theta, we know that that will evaluate to 1, and that any multiples on these If they are the same, we'll give the resulting output to like a root. So hold on, that's like a really bad way of putting it. Okay, so if you had, like let's say you want to get this value, to get that value out of that, in order to make this true, we know that we're building off of truth because our projection gave us r cosine phi, and then we divided r out of the system. So we know that we have to have cosine phi. So if we had, like if we just had this, the only way that this would work is if you had h squareds in here, and then you could factor those out. And so that would just be 1, and then the square root of h squared is h. So for any value that you want here, that is going to be what the multiples are in front of it. Again, this is our truth, and we're trying to adjust this to match that truth that we got through the definition of projections, which is like s is equal to what is it again? I wrote it down. It's the definition of projections was, yeah, it's right here. This guy. I worked through an example. Anyways, so if that's the case, we know that the solution to this is going to be C1 is equal to C2 is equal to cosine phi. And so now if we erase a bunch of this, we know the C. So what did we have before? We had C1 V1 plus C2 V2 is equal to V3. So we said that C1 is equal to C2 is equal to cosine phi. And remember, we had R in our system, so we will have cosine phi V1 plus cosine phi V2 is equal to V3. And that's just going to be, let's reintroduce R into our system. We had R cosine phi times cos theta 0. That was vector 1 plus R cos phi 0 sine theta. If we clean this up a little bit more, we can say that we have, and when we are working in strictly the xy plane, we would have phi is equal to 0, and we know that 0 degrees makes this just 1, so we end up with r cos theta, r sine theta. And then we can just factor out the r, cos theta sine theta. And if we were to change this system, now there's 2 to the n possibilities, where n is the dimension that we are working in, for possible systems that we can introduce. So so essentially what I'm saying is that if we're working in 3D, we can expect 2 angles, 2 to the n minus, 2 to the n minus 1 possible coordinate systems. I'm going to expand on what I mean by that. Okay, so when we're looking at this same diagram that we have, and we were to change just one of the conventions here. If phi is now a measure away from the x-plane, but we leave this one alone, this is possibility 2. I'm not going to go into possibility 3 and 4, but essentially for possibility 3 and 4, so we held this the same and used it here and here. Now, if we wanted the other 2 possibilities, you would take it as a measure in this direction, and then you would have this possibility, or this possibility. So anyways, so measure phi. And so if you had looking if we had a triangle here, you would have r cos phi here, and then r sine of phi here. And then we can also just complete a rectangle this way. And this part here, due to either, if you want to look at it as, we'll use the argument of symmetry again. This side here then is r sine phi, which means that this one here is r cos phi. And so now that we can go through that same steps that we have. We have this length here of r sine phi. And so if we just want to, if you look at that as the magnet, I mean, if we just jump straight to the Pythagorean theorem, we have r sine phi is equal to square root of cosine theta squared plus sine theta squared. And it's the same thing. If we expect to get r sine theta, that means that these two both have to be multiplied by r sine phi, which means here's something I was doing with all the possibilities that you can have. So we have, if we had a 2D table representing this, let's list out the 4 possibilities for what type of coordinate system we can have. Okay, so remember how I was talking about this before? This is wrong. I sat down and I spent some time trying to explore how many possibilities they were. And so I had some work I was doing here, which corresponded to those. I found out counterclockwise motion, clockwise motion, down and up. And I came up with the 4 possibilities here. We had, I'm just going to start thinking of these in terms of not rotations. Or, they still are rotations. I just don't want to use the terms clockwise and up and down. Yeah, so that was pretty much it. Here's possibility 1, 2, 3, and 4. These are the 4 different ways that we could set up a coordinate system. And my preference is to always use this one. Because everything's relative, I can define where I want the axes to lie for whatever problems I'm given. And then over here, this is just me musing about something. I was trying to look at this in terms of like patterns of how we would word things. You have an angle relative to an axis, and you have an angle relative to an axis, and another angle relative to a plane. And so I'm guessing that if the pattern continues, you would end up with an angle relative to a space, but I'm really not sure how that would work.